to all of you to this first webinar about a specific topic on the SPC5 power architecture family from ST. So the PLS as a tool vendor provides two tools or two debug tools for the SPC5 power architecture based family from ST. The first one is the SPC5 UDESDK, which is actually a ST product, but it is based on PLS technology. And of course, our universal debug engine, which is our key product and which is a professional full-featured debug, trace, and test tool that supports not only the SPC5, but also a wide range of multicore controllers and microcontrollers. I would like to start with an overview of what you can expect during this webinar. In the first part, I'm going to give you a short introduction into the SPC5 device family. I will also compare the two already mentioned debug tools, the UDE SDK and also the professional UDE version. And I'd like to show you how to benefit from our professional UDE version and from its features and functions for multicore debugging and also for tracing. And the second part, which will take the most of the time in today's webinar, I will show you the important functions for real-time or real multicore debugging, as well as for trace-based system analysis and real-time analysis of the SPC5 devices. I will also give you some hints how to deal with, for example, the GTM, which is also part of some of the SPC5 devices and which is often very interesting for developing especially automotive powertrain applications. So let's get started. In this slide on the left side, you see the principal architecture of this SPC5 power architecture-based automotive MCUs from ST. In this block diagram, you can see the main cores of the SPC5 based on the power architecture. Depending on the specific device, we find up to 3 E200 cores here in such a SPC5 device. There are devices available with lockstep. You can see this here in this diagram, the gray ones, so that ASIL level D can be achieved with such a device. We have also fast crossbars that ensure a high performance data transfer between the CPU cores as well as the peripherals. Not shown here in this diagram, but for some devices available is the GTM, the generic timer module, which is an IP core from Bosch. And this GTM provides optimized timer functions and signal generation as well as signal acquisition, especially for automotive powertrain applications. Also not shown in this diagram is the hardware security module that is also implemented on some of the SPC5 devices. For debugging purposes, interesting for us, the SPC5 has a JTAG interface so that the tool can access to the device using that debug channel. We have a debug infrastructure there, which is based on the Nexus specification and provides debug functionality like hardware breakpoints, memory accesses during runtime, and so on. You will find in some publications and also on the reference manual from ST the term 1CE, which is the marketing name for the debug development interface based on Nexus. On some devices, we find also a Nexus Class 3 Plus implementation. That means such devices provides program and also data trace. The trace can be recorded either into an internal on-chip memory, or it can be transferred off-chip at runtime using a parallel or a serial trace interface. As already said, we from PLS provide two tools for debugging the SPC5. Here you can see how the debug hardware part looks like. On the left side, the UDE SDK, and on the right side, the professional toolset. In both cases, the software part is based on the UDE user interface, and it looks like and feels like quite the same for both debug tools. And I'd like to show that in the demo afterwards. A few words to the UDE SDK from the hardware side. There is a small adapter that is connected on the OnCE JTAG connector on the board connected via USB to your PC. And the main limitation is that it can be only used for selected evaluation boards from ST. On the right side, you see an example how it looks like in the professional UDE version. Here we have our universal access device, one example of them, which is also connected using USB, or for other devices using Ethernet to your PC where the UDE is running. And then we have a target specific adapter which is connected also to the OnCE JTAG connector of the evaluation board from ST, or to your custom specific hardware. So there are no limitations on the target system here in this case. Here a short overview of the other devices we have. We already know the UET2 Pro from the slide before, which is the basic device in our family of 3 universal access devices. Besides the UET2 Pro, we have also the UET2 Next in the middle, which has a USB 3 as well as the Ethernet port and can be used also in your company network with that. You can, in addition to the debug functionality, add a plug-in trace module supporting different trace interfaces, and you can use this device to record trace data into an internal trace memory of about 512 megabyte. For this device, there is a so-called range extender available that allows debugging over distances of up to 2 meters between the base unit and the target device. And with the network capability, the range extender makes it the UED very perfect for test tracks with limited space. On the bottom, the UED3 Plus is a high-end trace device, and that allows capturing trace data into an internal memory of up to 4 gigabyte trace gigabyte. There are high bandwidth trace interfaces available for the UED3 Plus. For example, the serial trace based on the Aurora protocol, also used for some SPC5 devices, as well as parallel trace, which is also specified in the Nexus standard. Like the UED2 Next USB can be used to connect the device to your PC, or Ethernet is available. So after this short overview about the access devices, I'd like to come back to the two tools in this slide. I'd like to show you, or I'd like to compare the two tools, the UDESDK starter kit and the full-featured UDE version. You can see here that the UDESDK has some substantial limitations. Most important ones are you have only limited support for multicore systems or for multicore debugging. There is no trace at all, so you have only very limited possibilities for runtime analysis for your application. There is no scripting support, so this results in that you can't use the UDESDK for test automation and automated debugging. And the UDESDK is restricted to specific evaluation boards. I mentioned that before. So custom hardware is not supported at all. And also a very important key point, if you do professional development, the support services by us are very limited in the case of the UDESDK. SDK. So then let's have a look at some of the features of the professional UDE version that are missing in the UDESDK. So let's jump over to the UDE. I already opened the UDE, and we are ready to start from scratch. And the first thing I'd like to show you is how to set up a debug session. We call it workspace, and it's very easy and takes only a few steps. First thing that you have to do is create a new workspace using the file menu or the toolbar, and give it a name, for example, SPC5 webinar. And this is a file that can be saved on your PC. And then UDE asks for a so-called target configuration. A target configuration contains everything UDE needs to connect to a specific device, microcontroller from ST or from Infineon or NXP and so on. And we have a lot of default target configurations prepared for you. You see all the supported microcontroller architectures here. And we are looking for the PowerPC architectures and ST, and then we can select which board we have. This is a SPC. I type in SPC5 58NN, which is this one. I open that, and here I find some predefined target configurations for specific boards. I take this one, press finish, and then I can save this target configuration as a file also on your PC. I save it, and then I can select this target configuration. It can be reused by other workspaces, or you create, or you can edit it if you have a customized hardware. I can use it here in this case, press OK, and then UDE asks which cores of this SPC5 I want to debug. For now, I'd like to debug only the main cores based on the E200 Z4. I press OK, and then the UDE connects to the target system. Here you see some messages here which indicates a successful connection. And then I can load my application. Load program, select the ELF file or the hex file. ELF file contains also the debug information the debugger needs for presenting used variables, functions, source code, and so on. And then the so-called multi-core program loader gets opened, which is responsible or which allows to specify which core should load the application into the flash, for example, or into the internal RAM, and for which cores I'd like to see debug information. In the default case and for the SPC5, the core 2 is the main core, which is the only core which is active after reset or active after power on. And all the other cores, core 0 and core 1, are inactive at the moment. So we need core 2 to wake up the whole system. And that's why we program the binary only in core 2. For all the cores, including core 2, we want to load the debug information into the debugger. That is only visible by the debugger, and it's not written to the target system. So I leave this untouched. So blue means binary should be loaded. Green means debug information should be loaded into the debug tool. Press OK. And then automatically the flash tool gets opened and I can program the binary to the target. Then we are finished and we have a workspace, and we can now start the application and open some windows, for example, a watch window where we can add a variable, for example, this one, which is basically a simple counter. You can then enable the a periodic refresh for real-time watch. This is one of the advantages of the professional version. This is not possible in the UDE SDK. Okay, and then I can add some more windows and create a workspace which provides all the information that I need for debugging. I have already prepared such a workspace. You can close this one and save it for the next day, for example, save workspace or close it, and you will be asked to save the workspace, close it, and then I open a already prepared workspace for this demo here, which contains the application, which is the same that I have already loaded into the target. And I opened some more windows here. So I have the same configuration, the same target application. If I press OK, the flash tool gets opened. Now I'm sure the application is already programmed, so I can verify the contents of the flash memory. No differences were found. Everything is fine. I can close this and then I can start the application. So you see all the cores are running now. So the core 0, which is colored by this orange color here, has started all the other cores. You see the core state here in the toolbar, as well as on the bottom in the status bar, and you can see every core has its own color, and every window which is colored belongs to a specific core. Orange for core 2, green for core 0, and blue for core 1. Okay, then we can start debugging. The first is we can set, for example, a breakpoint in a function. For example, here every second we can jump to this function here and set a breakpoint here. And then you see if we hit the breakpoint, all cores are stopped instantly. So by default, we have a synchronized run control in UDE. That means if we break one core, all the other cores are halted as well, with a very short delay. This depends on the capabilities of the on-chip debug system based on the Nexus. Then I can start again, and you will see if we hit the breakpoint again, all cores are halted as well. If I have independent applications running on the several cores, then I'd like to have it decoupled, this synchronization. For this case, UDE provides a so-called Multicore Run Control Manager, which allows to group cores into a run control group, and all the cores in such a run control group are synchronized for debugging. Due to some hardware limitations by the power architecture and the implementation of the SPC5, it is not possible for the SPC5 to select only a few of the cores to be in a run control group. That's why I have only the possibility to enable the complete run control, the synchronized run control, or disable it completely. If I disable it and I disable the breakpoint, then you will see if I start the core 0, then core 0 is running, but all the other cores remains halted, and I have to enable or I have to start them manually. And if I set the breakpoint here again, then you see we stop in core 0, but core 1 and core in core 2, I stop in core 2, but core 0 and core 1 remains running. And if I want to set it back to the original state, then I have to stop all the cores manually, and then I can change the behavior of the run control management, the synchronization mechanism. I enable it again and start the application again. Sometimes I have, or very often, you have shared code that it is used by all the cores, and I would like to show how to deal with shared code. For that, I open some new code windows. I have it prepared, and I have put it in a so-called perspective that can be used in UDE to switch between some debug tasks and to focus on debug tasks. I have a default one, and I have, for example, a shared one, and in the shared perspective, I have added some more windows, which presents the same code but for the different cores here. You see we have an executed shared function, and if I switch to the so-called mixed mode, I see it is located on this address in the flash, and this code is the same and located the same flash address also for the core 0. And if I set a breakpoint here, then I hit this breakpoint in core 0, but switch back to the high-level language mode, and you see there's no breakpoint here for the core 0 and also not for the core 1. And if I use this breakpoint, I never hit this code in a core other than core 2. So then the easiest way would be at a breakpoint here and at a breakpoint here, and you have then also the code or the application stops if the other cores are executing this shared function here. But this would be very annoying. So there is another possibility. I can remove these breakpoints here, and then I can change the behavior of a breakpoint and check this multicore checkbox here, and then the icon looks a bit different, and we see that in all the cores for this shared function, we have set a breakpoint automatically, and you can unfold here this breakpoint in the breakpoint window and see which cores are affected by this breakpoint. And then I can start the application, and you see the breakpoint is hit if one of the cores are executing this shared function. This is a very nice feature, I think, and it's very useful if you have multi-core applications with shared code. Okay. Then at the very beginning, I decided not selecting the GTM for debugging, but I'd like to give you some hints how to debug if a GTM code is involved. So to enable the GTM debugging capabilities of UDE, you open the so-called target configuration, and then you can check the GTM if it's not already done during the setup of the debug session. Then UDE closes the workspace and load it again, and with the same application. And in this case, the application contains also code for the GTM. I have no source code for the GTM code, so I leave the symbols checkbox untouched, and I have to program. I don't have to program. I can verify the and exit the Flash tool, and then I have the GTM debugging capabilities of UDE enabled. So the GTM is also started by Core 2 by loading some code into the GTM RAM, which is handled by a init method. This is not important at the moment. But if I start running the application, you see that we hit a breakpoint, so that we see that the GTM is now running, started by Core 2. And yeah, it's running. The GTM itself provides no capabilities for debugging in the traditional way. That is the very important message for you. So no breakpointing, no single stepping is available. The GTM can be only halted. For example, if I press, for example, the hold button, so the GTM and everything else is halted in this case. Because of a hardware limitation, in this case, the GTM is in fact not part, that I have forgotten to say, is not part of the run control group by default, but due to a hardware limitation, the very first break of the system will also break GTM. But if I then start all the cores, the GTM remains halted. So and then I can, for example, open the code window of the GTM. You see no source code is available, only the assembler code is available. And you see, okay, the GTM is halted on this location here. And I can jump to so-called channels here. There are a lot of channel programs available in the GTM or programmed here. And with this, you can select which channel program you will be focused on. let's open a register window and browse in a register which indicates the running state, for example, MCS0, channel 0, register MCS0, channel 0, this one. Then we enable also the automatic refresh, and then we can see, okay, if I start this, the GTM, then it's running. And you can also put the GTM into the run control group. If I stop, for example, here the core, then the GTM remains running. If I stop the GTM manually, then I can add the GTM also to the run control group. And then if I start the GTM, everything is started. If I stop here, for example, at our breakpoint, then also the GTM is stopped. And if I remove the GTM from the run control group, then I can start the GTM and then also start the application on the main course. That's basically what you can expect from debugging GTM. For a real debugging of the GTM, only trace can be used, and I'd like to show it at the very end of this webinar, how it works. But before we try to trace GTM, I'd like to show you how to trace the SPC5 in general. So I mentioned before there is a Nexus Class 3 Plus implementation available on most of the SPC5 devices, which needs to be configured by the tool to get out some trace information. And now I'd like to show you how it looks like. So I have also prepared for that a new perspective in UDE with some windows which are useful if you do some trace-based debugging, trace-based measurements. Here on the right side, the trace window, obviously it's empty because we have nothing recorded at the moment, and also some other windows which performs some trace analysis. The first thing I'd like to do is we want to record a trace from, for example, starting from this function here. So I hit this breakpoint, and then we can jump to the trace window, and we need to configure the trace. This is the trace configuration dialog here for all the possible trace clients we have here in this target device. And we want to do a multi-core trace of all the cores, code trace, and I have to enable this here in this dialog. And we want to make sure that we have also timestamp information available, which is required by some trace-based analysis. So then I can start the trace using, for example, the toolbar, and then I have to start the application again. And the trace is automatically stopped because the trace buffer is filled completely. And you see here in the trace window the executed instructions beginning from the every second function here for all the cores, together with some timing information. But it looks very complicated, and there is another nice view available to get an idea about the runtime behavior of the system, the so-called execution sequence, where I can visualize the sequence of the executed functions. So I can open core 2, for example. Then I have here some code that is executed, and some functions that are called from other functions. And I can also open the other cores as well, zoom in and yeah, look for interesting points in the execution sequence. If you are looking for more specific things in your application, then some of the SPC5 provides some useful so-called cross-triggering mechanisms that you can use to specify trace sequences. So you can ask for if something happened on core 1, I'd like to start the trace on core 2, and after a certain time, I'd like to stop, for example, the trace and see what's happening on the target system. And for this, we provide another trace configuration tool like the UESK, which can be enabled using the config menu debug server configuration, and then you are looking for add-ins and trace and the nexus trace, and then you can change the configuration method from the dialog configuration to graphic configuration. Press OK, and then I can open a trace configuration, and it looks like different. So we have now the possibility to compose a trace task using this composer here. On the left side, we have a library of basic configuration tasks like set up the trace memory, enabling the timestamps, and then I can put another trace task which tells the trace system to start or stop the trace on a certain address or a certain function. Let me use the task 1 millisecond as a start event for starting the trace of core 2, and then I can start the trace. I have to disable the breakpoint, of course, start trace running, and then we see only for executed functions for core 2, and then I can start also the trace analysis in this execution sequence chart. And after some seconds, I get the execution sequence of my functions called by the task 1 millisecond. And I can use this, for example, to measure very roughly the time. Here we see we are about 1 millisecond between the two executions of the task 1 millisecond, as expected. And if I need some more detailed information about the call hierarchy and also about profiling, I can use this call graph analysis window here, select the core 2, start the analysis, and from this window I get also the information which function is called by which. For example, this one, the task 1 millisecond calls nested function 0 and then nested function 1 and so on. And this tab here provides a nice table showing some profiling information, which can also be sorted by the time, and you can easily find bottlenecks in your application. And finally, I'd like to come back to GTM debugging. Trace can also be used for debugging the GTM and for looking into, for example, interaction of the GTM with the main cores. And I use here another library which we provide with UDE, which is called the Advanced Library, which provides much more functionality also for tracing the main cores. but also for the GTM. And I have already prepared such a task which traces all the interaction between the GTM and the main core. It looks pretty much complicated, but it is quite simple. We have a state machine which waits for entering a function called handle GTM tasks, then starts some trace recording, and finally the trace recording is stopped if we leave this GTM task. Then we do also some data trace of the GTM and also of the core, and I limit the data trace or filter the data trace to a certain address range here. And this is only for providing some specific GTM information. I'd like to see the program trace of the MCS module channel 0 in this case. So everything is running, and then I can start the trace recording. And in this case, I'd need to stop it manually because there's no stop condition here. And go then to the bottom, and here I see in the bluish part, this is the executed GTM code. Here this question mark indicates no source code is available, and this this orange one is the code of the core 2. And we see here we have a data access which is sometimes not in the right order because of some FIFOs that we have in the trace system. That is also important to know, that you have to look a little bit in a wider range to find some correlations here. Okay, time is over. So I'd like to conclude a little bit and summarize what I have said. I think I gave you a good overview what is possible with the professional debug tooling for the SPC5 that you get with the UDE. Here highlighted the functions that I have shown to you during the demo. So multi-core support, trace capabilities I have shown, and also real-time watch for variables registers, and also memory is possible that I have not shown here. And also I have given you a short overview what is possible with GTM trace, because GTM debugging is not possible in a traditional way with the SPC5 devices. I'd like to highlight some features that I have not shown here during this webinar, which is the code coverage and also the scripting capabilities of UDE, which is not only related to SPC5, it's a general feature, and both of them will be addressed in the next 2 webinars, which are in 2 weeks and in 4 weeks. So you will get an invitation for these 2 webinars shortly. So that ends this webinar. If you have any questions, then please use the webinar panel to drop the questions or write us an email, and we will answer them offline. Thank you very much.